Hello, my name is Eric Green, and I'm a machine learning solutions architect for AWS. I work with public sector customers across the Asia-Pacific region, helping them solve their problems with machine learning and AI services on AWS. My colleague, Pauline Kelly, a public sector solutions architect, has also been working with customers on machine learning problems. We are both excited to be able to talk to you today about bias and explainability in machine learning. It's a key issue we've seen many AWS customers concerned about across a wide range of industries. AI and machine learning is helping to solve high-value problems for many AWS customers. Predictive models can be used to better market products, to create natural interactions, to automate processes, and to create whole new types of solutions. Now, as the adoption of machine learning and AI becomes more widespread, its impact on our day-to-day lives is also becoming greater. AI makes decisions on our creditworthiness, determines how we are marketed to, what online content we can see, and can even influence the quality of education and our healthcare. Now, given the importance of some of these decisions, a key question many of our customers have is how do they ensure their machine learning models are fair? Now, in this session, we're going to discuss the concepts of fairness in machine learning and how bias detection and explainability can be integrated into an organization's best practices for machine learning to meet the requirements for fairness. So we have a lot of things to cover in today's talk. I will start off by explaining what we mean when we say bias in data in machine learning. Then I will discuss how fairness, accountability, and transparency are important in building successful ML applications. Diving deeper into the topic of transparency, I will discuss explainable machine learning models. Pauline will then talk about how Amazon Clarifai can help you to integrate these bias and explainability features into your ML processes and ML ops infrastructure. Pauline will also demo Clarifai to show you these features in action. I'll then finish with some more resources to get you started in Amazon Clarifai and machine learning. So the first thing we need to establish is what we mean by bias. Let's start with a simple definition of bias, of which there are two main types. The type of bias most people are familiar with is a prejudice for or against a person or a group of people in ways that are considered to be unfair. Now, this type of bias can be inherent to the data being collected, regardless of your collection methods. The second definition of bias is a scientific term that means the data you collect does not exactly match the real-world data, regardless of whether it contains inherent bias. This is known as data bias. Machine learning algorithms are trained with data, and since almost any data set is bound to have some form of bias, machine learning models will also give bias predictions. Now, machine learning allows us to significantly automate decision-making processes, so machine learning models can strongly amplify unfair outcomes if the underlying data is biased. Also, a machine learning model will skew its predictions towards the majority classes of data to optimize its accuracy metrics. This means class imbalances in the data can result in models that is even more biased. So why is bias important? Bias issues occur in most domains that directly affect your customers. In financial services, bias can affect credit decisions such as granting of loans, credit limits, and setting of interest rates. Bias impacts which products are marketed to us and how. Bias can impact how we are tested in school and which education programs are open to us. And bias can even impact our access to government services and determine wide-ranging government policy. Now, biased data can cause misdiagnosis, incorrect treatment plans, and many other issues in healthcare as well. Now, these are just a few of the important domains that biased data and machine learning models can impact that highlights the importance of understanding and mitigating its impact. Now, the first step in mitigating bias is to analyze what the biases are in our data. So let's walk through some of the types of bias. Now, in practical terms, no data set can be completely free from bias. First of all, the underlying process and instruments used to collect data can introduce systematic errors. As an example, let's say that I'm an administrator collecting data on students with a goal to identifying those most likely to succeed. Now, I have a data set composed of final grades and demographic information for each student from the last 5 years. The information gathered includes features for age, gender, parental education level, and the final grade they received. The final grades for some of these years' students doesn't include final exam results, as their course was still in progress. Now for this reason, their final grades are almost 20% lower than the actual grade. Thus we have a systemic error in that some students have an incorrect final grade. Now when collecting data, it is usually not practical to measure all the quantities that represent the real world. You need to select the features to measure that are aligned with what you're trying to accomplish. Now the choice of attributes that are measured impacts what the data can be used for. Since we're only collecting a limited set of features, some important ones are missed. For example, we don't know if students have any health conditions that may have impacted on their final grade, since we didn't include that feature in our data. It's also usually impractical to collect selected features across the entire population of all of history. You need to collect a subset that limits the amount of data, but is still representative of the real world. Now, how your data is sampled can introduce sampling bias. For example, during our data collection efforts, the math professor was on vacation, and we did not receive any data for her students. So unfortunately, we have no data for any math students and have a sampling bias. In addition to the inherent biases in the real-world data we are collecting, the human decisions you make in designing your data collection systems, what features you measure, and how you sample your data can all introduce human biases into the data. Now, for example, teachers tended to give students whose parents previously attended the school higher grades. This human bias resulted in data that was biased for parental education. Now, these are just some of the main ways bias can be present in your data. If we did nothing to correct for any of the data biases, and then we trained a machine learning model to predict final grades based on our collected metrics, the machine learning model would be biased due to all the biases in the data. This can lead to unfair outcomes due to changes in admissions and also lead to the school not achieving the outcomes they expect. Now, detecting bias in data begins with analyzing the distribution of data across attributes that require special attention. This can help determine any bias issues you will have with your machine learning model. Now, for our school example, we could analyze the distribution of students based on the important characteristics like gender, age, and parental education. Looking at this distribution of data, you can see that our data is skewed towards female students between 18 and 30 years old with parents that have no college education. This means our machine learning model will work best when predicting the final grades for these types of students, as it has more training data for them. Now, this class imbalance in our data results in skewed results with our machine learning model. This algorithmic bias can give the false perception of having a highly accurate model, when in actuality the model does not work well for all students. The world is always changing, and a machine learning model trained on a data set will experience drift as the data changes over time. For example, in the school, students are constantly being recruited or graduating from school. This will change the distribution of students over time, as well as the biases in the data. So let's talk about some of the tenets used to ensure fair ML outcomes. So making machine learning models fair requires understanding your data and the machine learning models trained from them. Data and models need to be analyzed for bias, changes in data distribution over time need to be monitored, and adjustments to the data are needed when issues are discovered. Starting with data, one of the best ways to address bias is to collect more data. This can mean more samples of data or more features that better represent the underrepresented. New data also needs to be further evaluated to discover any new biases that may be introduced. You can also adjust the balance of data for underrepresented classes by using data augmentation techniques or filtering out overrepresented data. When training the machine learning model, you can also build in fairness by creating metrics for fairness and optimizing for them during training. You can also train several different models with different algorithms, features, or data inputs and select the best model based on fairness criteria. Now, once a model is deployed, you still need to constantly monitor them for changes to ensure they are still meeting your fairness constraints. Now, the development and operations process to build, deploy, and monitor ML models needs to account for changes and to be able to retrain and redeploy quickly when issues are detected. Historical decisions need to be centrally stored so you can create analytics and reporting to help guide changes to improve that fairness. So let's talk about accountability when it comes to machine learning and automated decisions. Accountability means the process to apply decisions from automation and machine learning leaves us an escalation process for anyone affected by a decision. This means the ability to escalate to a human and a process in place that allows adverse decisions to be contested. Now again, storing the historical events from this process and the related decisions can help create analytics and reporting to help guide changes to improve the overall process. Let's talk about transparency machine learning. Now, transparency means the process for arriving at decisions is understood internally and can be explained to the affected parties. This means within your organization, you have an understanding of how the model works in a general sense, and it's interpretable. You also need to have a well-documented process for how ML decisions are applied. This means understanding the additional logic involved in the decision process, as well as the human processes. Now, it's also important that you can explain individual decisions to customers and that ML decisions are explainable. Now, explaining how a machine learning model makes predictions can help to understand any biases in the model, and is also key to gaining the trust of those affected by the decision. Now, with linear models, where a prediction is made from a sum of weighted features, explainability is simple, as you can just look at the weights. For example, if our school success model was a linear regression model, interpreting the model and explaining this decision is simple. The weight applied to each feature directly represents the importance for any success predictions made. Now, for this example, gender and parent education would have the most influence on the school success prediction. Now, there's a trade-off between explainability and accuracy in machine learning. Linear models are easier to interpret and explain, but are usually not that accurate as other types of nonlinear models, such as boosted trees, SVMs, or neural networks. For example, if a more accurate model for school success included cross-correlated or exponential features, arriving at features importance is not as simple. There are techniques for generating feature importance for more complicated models. One of these is SHAP, a method that can be applied to complex models to determine the importance of each feature on a machine learning model's predictions. SHAP is model agnostic, meaning it doesn't need to know the internals of a machine learning model, and can be used with any type of machine learning algorithm. Now, SHAP does not explain every prediction a model makes. It only tells you what features were important for a single prediction or a set of predictions. This means it's a local interpretation of a machine learning model. Global interpretations can be estimated by using a subsample of data, but the variance of the estimated importance will increase with sample size. So how can you integrate bias detection and explainability into your machine learning process? I'm going to hand over to Pauline Kelly to talk more about Amazon Clarifai, which provides an end-to-end solution to help you mitigate bias in machine learning and provide transparency across the entire machine learning workflow.
Thanks, Eric. Clarifai is a new feature of SageMaker that detects biases in your data and machine learning model, and also provides explanation metrics for model predictions. Clarifai works throughout the machine learning process to help you identify and mitigate bias. Clarifai helps identify bias during data preparation. You specify sensitive attributes, such as gender or age, to Clarifai, and it runs a set of algorithms to obtain different measures of bias. After the algorithm runs, Clarifai provides a visual report with a description of the biases and their severity, so you can take steps to mitigate. Since bias can be introduced during model training, Clarifai also checks your trained machine learning model for biases. After a model has been trained, you identify attributes to check for bias. Clarifai then runs bias detection algorithms and provides you with a visual report on the biases for each attribute that you specified. Trained models will consider some model inputs more strongly than others when generating predictions. Clarifai generates a report showing the importance of each input for the model's overall decision-making process. These details help meet compliance requirements or determine if a particular model input has more influence than it should on overall model behavior. Clarifai also provides an API to produce explanations on individual model decisions. Explaining why a model made a specific prediction helps to build trust in the overall decision-making process. Clarifai is integrated with SageMaker Model Monitor, so you will become aware if there are shifts in the importance of model inputs that could cause model behavior to change. This brings automated bias detection into your MLOps processes. Clarifai outputs the bias and explainability results as visual reports. You'll be able to provide these reports to internal stakeholders and auditors to meet compliance requirements. Zopa is an example of how Clarifai is being used today. Zopa is a digital bank that uses machine learning to identify possible fraud in their loan applications. They need explainability for their internal compliance and data science teams and for future regulatory requirements. With Amazon SageMaker Clarify, they can now produce model explanations more quickly and seamlessly. So let's see Clarify in action and open up SageMaker Studio to see how Clarify generates bias and explainability reports. Keeping with the example that Eric introduced previously, we're going to explore a student performance dataset from UC Irvine. In this dataset, we have various features for students, like age, gender, and parent education level. The label we want to predict are the final grades, which range from 0 to 20. Before we start, we should always give some thought to what our data is. Is our dataset representative of different groups? Are there known biases in how the data was collected? And does the data need to be modified to mitigate bias? In this notebook, I'm using Pandas to look at the features for this dataset. As you can see, there are a number of features like sex and age that are sensitive. In the open source student performance dataset schema, this attribute is being denoted as a binary data type. It is well established that there should be more than 2 possible values here. This is likely to be an example of human bias, where the student may have only been able to enter one of 2 values. We need to keep in mind any human biases that may be present in our data in relation to these features. Clarify will help us find where there may be biases in this data throughout the machine learning process. To speed up this demo, I've already pre-processed the data and reformatted it for machine learning. I've also split the data into training and validation sets and uploaded them to S3. In order to create a pre-training bias report, we will call the Clarify API. We can use it to configure and run Clarify jobs, and this will run as a SageMaker processing job. Before running the pre-training bias job, we need to define the data configuration, which specifies where the data to analyze is in S3 and where to put the final report. We also need to specify what we are predicting, the features, and what type of data set this is. In my case, I've specified where in S3 my training data was uploaded to, where in S3 my reports should go, that my label is the final grade, and the headers are taken from the training dataset, which is a CSV file. Next, we configure the bias detection settings. This is where we define the range of possible values for attributes that we are interested in. Since the grades between 15 and 20 are the most favorable outcomes, we define a label value threshold. We also need to define the facets. Facets are the sensitive columns that we want to monitor for bias. The facet name we will specify is gender. For some bias metrics, you will need to provide a feature to group by. We are now going to run the Clarify job. We could specify when we run the job to only collect a subset of the bias metrics to save on time, and for our run, we're going to collect all of them. For this dataset, Clarify ran for 5 minutes with a processing time of 23.39 seconds. For other instance types or dataset sizes, this time will vary. But to save on time, let's review a run that I've done previously. Let's have a look at the output of the Clarify job. In our data, 0 represents a male student and 1 represents a female student. One of the bias metrics that Clarify gives us is on class imbalance. This metric allows us to see if we have more data for males or for females. A perfectly balanced class will give a metric of 0, whereas all males would be +1 and all females would be -1. For this report, we can see that the class imbalance metric for gender is 0.04, which means we have fairly good balance. For other data sets and features, this may not always be the case, and we would need to either collect more real-world data or apply synthetic data creation techniques like SMOTE. Another metric is the difference in positive proportions in labels, or DPL. For our data, this will measure the proportion of male students that got good grades compared to female students that got good grades. The value here is -0.079. This is very close to 0, so we have parity here. If this value was further from 0, we would have a bias in the data that we would need to further analyze. This could be due to historic data biases inherent in the data, sampling biases, or any of the other biases that Eric discussed earlier. Let's have a look at how we can generate post-training reports. For this example, we are using the XGBoost algorithm to train our machine learning model. Clarifai will work with any machine learning model, including SageMaker built-in algorithms, as well as any other third-party algorithms. During model training, we are using the root mean squared error, or RMSE, to optimize the parameters of the model when training. We could also add in a fairness metric to maximize for during the training process that could improve model bias. This is out of scope for the demo, but it could be implemented within a SageMaker training job. Model training and optimization on this dataset with XGBoost takes around 4 minutes. I already have a model ready to analyze with Clarifai. To configure the post-training bias job, we need to add a model configuration as well as the data and bias configuration. The model configuration specifies where the model is located in S3, as well as the instance type and the quantity to spin up for the job. The instance type and the quantity should be set based on your business needs for Clarifai's processing time. For the demo, we will just use a single small instance. We can now run the model analysis. Clarifai will stand up an ephemeral model endpoint and run inferences through it to generate analysis for its model bias and explainability reports. For our dataset, Clarifai took 12 minutes to run. Depending on the data size, the instance configuration, and the amount of data, this time will vary. I have previously run a model analysis, so we can skip waiting and go straight to the reports. Looking at the analysis, we can already see some issues with our model. The disparate impact, or DI, is the ratio of positive predictions for the different facets. For our example, this is a measure of how many male students are predicted as having positive outcomes compared to female students. As you can see in this report, this is 1.7, which means that the model is predicting positive outcomes 1.7 more times for male students than for female students. Another measure is the difference in conditional acceptance, or DCA. This is calculated by comparing the ratio of actual positive outcomes predicted between the different facets. From this report, we can see that male students are predicted by our model to have better grades 27.5% more than female students. There are many other measures available, and they're all explained in the Clarifai documentation. Now that we've discovered some biases in our model, let's dive deeper and explain what the model is using to make decisions. Let's generate an explainability report that produces SHAP values for our model. SHAP values show us the relative importance of input features for model predictions. To run a Clarifai explainability job, we need to specify the SHAP configuration. The configuration specifies the baseline, the number of samples, and the aggregation method. The baseline determines what hypothetical example Clarifai will compare against when explaining feature importance. For our example baseline, we are just using the first sample in our validation set, and this is what we show in our documentation. However, in practice, you would create an average instance of a student with the mean or median value for the numerical feature and the mode for categorical features. We will use 15 samples from the dataset and aggregate the results based on the mean of the absolute SHAP values. You can now call the Run Explainability API, passing in our data, our model, and our SHAP configurations. This will generate the explainability report. Looking at the explainability report, we can see that absences had 7 times greater feature attribution than the next most important feature. So, given this knowledge, we may want to dive deeper and see if higher absences from female students is having an adverse impact on the model predictions. We could then choose to either remove this feature as it results in unfair outcomes, or find additional features that the model can use to lessen the impact of this feature. Now that we've done our analysis with Clarifai, we can iterate until we are comfortable with how our model is performing, and then deploy the model into production. Once it's deployed, we still need to monitor it to ensure it performs to our expectations, and this is where Model Monitor comes in. That's it for the demo. Let's jump back into the presentation. Let's look at how Clarifai integrates with the machine learning lifecycle and MLOps infrastructure. Amazon SageMaker Clarifai works across the entire machine learning workflow to implement bias detection and explainability. When preparing and collecting data, Clarifai can look for bias in your initial dataset as a part of SageMaker Data Wrangler. When tuning and training your models, Clarifai can check for bias in your trained model as a part of SageMaker Experiments and can also explain the overall behavior of your model. Prior to production, Clarifai reports are used to evaluate and qualify the model for deployment. Once models are deployed, Clarifai can provide explanations for individual inferences made by your deployed model. Clarifai also extends SageMaker Model Monitor to check for changes in bias or explainability over time in your deployed model. Let's look at a SageMaker MLOps architecture. During data wrangling, typically you would work with SageMaker Data Wrangler and use S3 to hold the generated features. You would then run Clarifai on your data to create data bias reports that are also stored in S3. Next, you would train your machine learning model with SageMaker and place it into your model repository. Then, with the trained model, you create Clarifai model bias and explainability reports. All of these steps, from data wrangling to training, as well as generating bias and explainability reports, can be executed as a SageMaker training pipeline. After reviewing the reports, if the model meets an established fairness criteria, you can approve it for deployment and execute the SageMaker pipeline for deployment. Once you have the production endpoint running, you can collect bias, explainability, and other model quality metrics on a regular basis with SageMaker Model Monitor. Using a defined baseline for your metrics, you can also set up automated checks in CloudWatch to alert you if model drifts occur, and even re-trigger your CI/CD process to automatically retrain your models. That's it from me. I'm now going to hand over to Eric to go through the resources and finish off this section. Thank you.
Thanks, Pauline. So let's go over some of the resources you can use to get started with machine learning in SageMaker Clarifai. For more information about Amazon SageMaker Clarifai, go to aws.amazon.com/SageMaker/Clarifai. It has plenty of links to service documentation, blogs describing ways in which the service can be leveraged, and also existing customer use cases, all available from there. Also, visit the AWS AI and Machine Learning Resource Hub and learn how to use AI and machine learning to accelerate your machine learning journey. You can also find out how to build your own machine learning skills with digital training courses, classroom trainings, and certification for machine learning by visiting this link here, aws.training/machine-learning. Thank you again for attending. We really appreciate your feedback so we can better understand the topics and services you'd like to know more about. Now, thank you from Pauline and myself, and have a great time at Summit Online.